Hi, so in this talk, which is a practice talk for a talk I'm about to give in a week, I'm going to look at a study of guts. And before we get into the details of what I'm actually going to talk about, let me start with a little disclaimer. I know that my accent is perhaps annoying or unusual to some people who's listening to this talk, and I realize that at some points I might speak a bit quickly. If there is something that is unclear in this talk, just ask and I will try and make it clearer, and I'll try and explain what I was trying to say. The second part of this is that I am dyslexic, and part of that is not being able to pronounce names properly. So there are going to be names in this talk which I'm also going to say wrong. So let's begin. This talk is going to be split into two halves. And the reason I've done this is that the average attention span of a person, although the best length of time for a talk is about 18 minutes long. And physics seminars, they tend to be an hour long. So what I usually do is I split the talk in half into two 30-minute chunks or 25-minute chunks. And then they can be, these two halves can really be considered as separate talks joined by a common theme. In the middle, I'll do something called a brain break, where we will just stop and we won't think about physics, or think about something fun. The first half of this talk is going to be based on the guts of SU48. Now, this is something that I will explain what it means as we progress through this talk. Basically, what we are going to do is we're going to find, or we're going to discuss how we find all semi-simple subalgebras of SU48, which contain the standard model. This is based on a paper I did with Ben Alenak and Ben Kopias at the University of Cambridge. The second half of the talk, what we're going to do is we're going to take one of these guts, these grand unified theories, and we're going to study it in more detail. And the example that we are going to choose is going to be SU4 plus SP6 plus SP6. And I'll explain why this is the one we chose, and we'll go into the nitty-gritty details, or not the nitty-gritty details, but I'll give you like enough information so you understand what we did in that paper. So let's proceed with the first half of this talk. I'm going to flash up some code. This is some code, and this is really the product of this first half. This is the product of that paper. I'm not going to tell you exactly how this code works, but I want to give you in this first half of the talk an idea of where this code comes from and the sorts of features that it has. As you can see, the code is fairly long. It's about 4,000 lines long. And this is just one file. It's also like .h files there as well. So it's a fairly bit of a involved set of code, but I'm going to tell you the story of how this code came to being, it came into being, and what it does. So where does the story begin? The story begins in this building. So this is the Cavendish Laboratory, and I realize it just looks like a block of concrete with some windows in. Not only does it just look like a block of concrete, it's also an asbestos-filled block of concrete. So not only is it ugly, but it's also potentially deadly. And this is where I did my PhD, and this is where the story of this code starts. Because on every Wednesday morning, when I was a PhD student at Cambridge, we used to have this meeting, and it used to be called the SUSY Working Group. And in this meeting, everyone in Cambridge, all of the Pheno people at Cambridge would get together and they would start to talk about, or they would talk about the things they had done that week and things that they were interested in. They ended up changing the name because no one was actually talking about SUSY, and they didn't really want to give it bad publicity by calling it the SUSY Working Group, like this is what the main thing that we were talking about. So they ended up changing it to the Cambridge Pheno Working Group. On this particularly rainy Wednesday morning in 2018, there are 3 people in this meeting of interest to this story. There is Ben Alenak, Joe DeFigi, and Scott Malthow. And they were having this discussion amongst themselves, and they were trying to ask themselves a question, or they were looking at a paper related to, or they were writing a paper related to this question. They were asking, for the standard model plus 3 right-handed neutrinos, what are the anomaly-free sets of charge assignments under a U1 extension. Okay, so that might be a bit technical, but this is just related to a C prime model. So it's basically asking what happens when you take a C prime model and add it, or a C prime and add it to the standard model. But let me drag this out even further and let me break this down into a more precise statement. So this is the standard model. I have literally just written the standard model here. I've written the quarks. I haven't written down the Higgs, but it's just the quark sector, sorry, the fermionic sector of the standard model. The farthest column to the right are the right-handed neutrinos. So what Ben, Joe, and Scott were looking at was the standard model plus 3 right-handed neutrinos, which is this thing here, and the corresponding fermionic content. And what they were doing is they were considering what happens when you add an extra U1. Okay, so they took their standard model gauge group, which is this SU3 plus SU2 plus U1, and they added an extra U1. So they considered the second box. And notice when you've added this U1, each of your particles gains a new charge with respect to this U1. So your quarks gain a charge Q1, Q2, Q3. Your up-type quarks gain a charge U1, U2, U3, and so on and so forth. Now I have not assumed universality, charge universality. So I've let my, or family universality rather, I've let my charges be different amongst the families. And these charges can be integers. And what we want is, or what Ben, Scott, and Joe wanted, is these charges to be anomaly free. So anomaly freeness is basically a set of conditions that come from triangle diagrams, or if you want to be technical, index theorems and topology. There are a set of conditions that this theory has to be anomaly free, and those conditions can be surmised into a set of equations, which are these equations here. Now, these are polynomial equations, as can be seen in integers, the charges. The charges, like I said, we kind of assume they're integers. So we want to solve these equations. Now, polynomial equations in the integers have a very special name. They are called Diophantine equations. Diophantine was this Greek mathematician, and he was perhaps one of the less well-known of the Greek mathematicians, the Greek philosophers, let's say. And he was basically one of the forefounders of number theory. In fact, do you know Fermat's last theorem? He wrote something in the margin of a book. It was Diophantine's book that was written in. It was in the margin of Diophantine's Arithmetica. And this makes sense because Fermat's last theorem is an example of a Diophantine equation, which shows actually how difficult these equations are to solve. Okay, so this is what Ben, Scott, and Joe were doing. They were looking at these equations, and they were trying to solve them. And they did what is perhaps the most natural thing to do when faced with such equations. They solved it numerically. These equations are called the ACCs, so I'm going to use ACCs to abbreviate, but that just means the set of equations. And they solved these equations numerically. In other words, they chose some maximum charge. They said, we're not going to let any of the charges be above this value, and we're just going to scan through them, and we're just going to find the solutions in that way. And that's what they did. And they produced this paper. The arXiv number is the top one, and they had all of these solutions. And I was listening to this in this working group, in this meeting on this Wednesday morning, this rainy Wednesday morning in 2018. And I was interested in what they were saying, not really understanding it, but, you know, absorbing the information in by osmosis. As 2018 turned into 2019, a collaboration this side of the Atlantic in America published another paper. This collaboration consisted of Costa, Dabrowski, and Fox, and I apologize to them if I pronounce their names wrong. Paddy Fox actually had the pleasure, let's call it, I wouldn't call it a pleasure, maybe not, of reading my PhD thesis. But they were looking at something very similar. They weren't considering the standard model plus U1. They were considering the U1 anomalies. So that's just a U1 gauge theory, not connected to the standard model in any way, a U1 gauge theory where your fermions have charge xi, and they were trying to solve the anomaly equations corresponded to that situation, which are these here, this sum of xi's and the sum of xi's cubes equal to 0. And they managed amazingly, to find an analytic solution to these equations. So I was in Cambridge having listened to this discussion by Ben, Joe, and Scott, and this paper by Costa, Dabrowski, and Fox came out. And at this time I had worked mainly on more formal projects. So I was like to Ben Alnuk and Ben Kupias, my supervisor, can I have a morphinoid project? And they were like, sure, why don't you do a project related to VC1 anomaly equations? The project ended up being more number theoretic than Pheno, but what we did is we managed to solve these equations. We managed to solve these equations analytically, the standard model plus U1. And just to quantify what this means, it basically means that we have a classification of every single U1 extension of the standard model, which is anomaly free. If you give me the set of parameters which we use to parameterize the solution, I will output a set of anomaly free charges, and every set of anomaly free charges can be found in that way. So basically, the standard model plus U1 extensions have been classified completely. That is a done problem. So it's 2019, it turned into 2020. There was a dramatic shift in the world. I moved from Cambridge back up to my parents' house in New York, and I was looking for something new to do. I had published this paper in the latter half of 2019. I was looking for something else to do, something related to this U1 extension, something related to gauge groups. Now, to tell you what me, Ben, and Ben, the two Bens, tell you what we ended up focusing on, what we ended up looking at, I need to give you like a 2-minute lecture in Lie algebras. Now, it's not going to be like a detailed lecture. It's just going to be enough so that you can follow what's about to come. I just need you to know what a simple Lie algebra is. Now, a simple Lie algebra is basically all of the Lie algebras that you're secretly quite familiar with. Things like SUN, SON, SPN. SPN you might not be so familiar with. I'm going to tell you what that is later on in the course, because that is going to be part, not course, the lecture, this talk, the second half of this talk. I'll tell you what SPN is. But you just need to know that all of those sorts of algebras, they are called simple. There's a larger category, not a category, but larger collection of algebras called the semi-simple algebras, or the semi-simple Lie algebras, and they are ones which can be written as the direct sum of simple factors. So for example, the SU3 plus SU2 of the standard model, that's called semi-simple. And the SU4 plus SU2 plus SU2 of Pati-Salam, that is also semi-simple, because it can be written in this way as a direct product of these sorts of algebras, things like SU4 and SU2. At the level of Lie groups, this will correspond to like SU4 cross SU2 cross SU2. There is a bigger collection, even than semi-simple Lie algebras, which very few people ever really talk about, and this is called reductive Lie algebras. So there are two reductive Lie algebras which you might be familiar with as a particle physicists, as phenomenologists. They are, of course, the standard model. The standard model is an example of a reductive Lie algebra, SU3 plus SU2 plus U1. What reductive means is it means it's semi-simple plus some U1 factors. So it's a combination of simple Lie algebras, simple ideals, as they're called, plus U1 factors. The other example you might be familiar with is this 4-3-2-1 model, which has been used as model building, as motivation for model building. Okay, so now we've had this 2-minute lecture into Lie algebras. Let me motivate what we did. Let's take SO10. So SO10 is it's a familiar gut that you might be familiar with. It's a familiar gut. And you can form this sort of triangle. So at the bottom left-hand corner, we have the standard model. Okay. And at the bottom right-hand corner, we have SU48. Now, SU48, the 48, where does that come from? That's just the number of fermions in the standard model plus the 3 right-hand neutrinos. So that's like the total dimension of the fermionic sector. So that's where the SU48 comes. And this map across gamma, this is the representations of the fermions. All of the information about the 3-2-1 representation of the left-handed quarks, all of that is just in the map gamma. And that's really all this map gamma is. It's the representation of the fermions, the fermionic representation standard model. Now we can form this diagram. We have this gut called SO10, and SO10 can be embedded into SU48 for 3 copies of this 16 representation. So this is like 16, all of the fermions sit in one family, sit into one of the 16s, but we need 3 of them, and they can all be fit into this 16, the 3 representation. And that provides an embedding or a map from this SO10 to the SU48. There is then another map alpha, which is how the standard model fits into the SO10, which makes this whole diagram commute. And what the question we decided to ask is, you know, this is one example of such a diagram, but we can ask for other examples, right? We can ask, what are all possible diagrams of this sort? And now, one example for G in this diagram, G can be really any Lie algebra at this point. One example of G can be, for example, the U1 extensions we just discussed, and that they provide one class of G you can stick there. And what we want to do is we want to consider another class of G, another class that we can quantify and that we can classify and we can list. The holy grail of the study would be to try and find all such diagrams where G is reductive. Now, this is whether this task is possible is a difficult question. It probably is possible. It's probably a lot of work. It hasn't been done. It's never been done. And it's probably an interesting thing. Maybe it's an interesting thing to do at some point, but it's difficult. It's not that easy. What we can do, though, is we can ask for G to be semi-simple and for it to be free of local anomalies. So there are 2 conditions that we can put on G. And we can ask, you know, can we try and find all of the diagrams that look like this? All of the kind of like guts. Basically, what this corresponds to is finding all of the guts, the semi-simple guts, which embed into SU48, so don't require any more fermions that are anomaly free. So we can ask ourselves, is this possible? How do we know that it's possible to find all of these guts? How do we know it's possible to find all of these triangles? And we know because of the work of these 3 people. Well, the work of more people in this, but let me just take these 3 as an example. They, Dinkin especially, really were the forefathers, well, Dinkin mainly here, Lorentz and Grubner, they have similar papers, and there's like some overlap between what Grubner and Lorentz did, I'm not pronouncing those names right, and what Dinkin did. But they collectively worked on Lie algebras and subalgebras of semi-simple Lie algebras, as you can see by these paper titles. So their work basically meant that this task of finding all of these G's was basically a well-known, a mathematically doable problem in mathematics from the 70s and the 50s. So there's really no new mathematics has to come in to finding all of these diagrams. It's just a case of doing it. It's just a case of writing the code and getting it to work. So that is exactly what we did. And that code that I mentioned earlier, that basically does this brute force. It basically helps find all of these guts. So let's just ignore the fact that this is possible. It is possible, and you can do it, and you can write the code. And it outputs a solution. So what is that solution? Let's look at the 1 family case. For the 1 family case, there are 3 possible G's that can be. So there are 3 possible guts that don't require any additional fermions other than the 1 family of the standard model plus 1 right-handed neutrino. And as this diagram suggests, they are SU5, SO10, and Pati-Salam. This is why these are really the famous ones. These are the ones you've probably heard of, because they are the ones which 1 family, and there are no more. That's really it. Notice I've drawn 2 lines, and this is because the SU5 gut and the SU4 plus SU2 plus SU2 gut, they both are subguts or subalgebras of this SO10 gut. So really, we can call the SO10 one a maximal one because the other 2 fit into it. And most of the time, we're really interested in these maximal guts. There are often quite a lot of guts that fit into them. But for what I'm going to show you, let's just focus on the maximal one. So in the 1 family case, there is one maximal one, which corresponds to SO10. Let's turn to 2 families. Things get a bit more interesting here. In 2 families, there are 45 algebras altogether. And here are some examples. There's SU4 plus SP4 plus SP4. Now, I've also written the representation down because in some cases, the gut is not just specified by the Lie algebra. You also have to specify that map that I called beta. You also have to specify the representation of the gut. So this is one example of a gut, and this will actually be important for the second half of the talk, because our gut will be the free family generalization of this. This is things like SO10 plus SU2, where like the SU2 is like a family symmetry, and the SO10 is the usual SO10 gut, and other generalizations. SU8 plus SU2 plus SU2, we'll discuss the free family version of that in more detail. So what about the free family case? There are 340 algebras altogether and 24 maximal ones. These are the 24 maximal ones. 24 is just enough that I can fit them onto one slide, which I was happy about, although it took some editing in Keynote to get this to work. But these are the 24 guts. Oh, and I haven't put the section title for this slide. That's on my to-do list. Okay, so there are things which are pretty boring, like SO10 cubed. It's unsurprising that that is a valid gut for free families. There are slightly more interesting things like SU12 plus SU2 plus SU2. We're going to discuss that in the second half in more detail, but this is really the result. Okay, so this is like the end of the first half. Let me just give you the 3 takeaway points. So really, what should you take away in your heart of hearts from this first half of the talk? The first thing is that progress has been made in classifying guts, right? We classified all of the guts given some conditions, and that conditions were basically that it had to be anomaly free, there couldn't be any more fermions, and it had to be semi-simple. So they were really the 3 conditions, and given those conditions, there were exactly 340 of them, 24 of which were maximal, but they were all based on really like kind of familiar themes. You probably could have guessed them all. The part code checks, you know, there are no more than this, but you could have probably, if I forced you to guess of all of the 340 of them. And I think it's important to mention, this is one of the 3 takeaway points, that we didn't say anything about scalars. So I'm not saying anything about the scalar content of this model. I am just talking about fermions. I just talked about fermions. I never said anything about scalars. I should have probably said that earlier on in this talk, but forgive me for that mistake. So let us progress into that little, you know, I said in the middle of the talk, we're going to do what I'm going to call a brain break. We are now at the time to have that brain break, so you can switch off for a second. I'm not really going to talk about physics. I'm going to talk about something fun. And this slide is the fun thing. It doesn't look very fun, but let me explain. After we had been working on this paper, after I had spoken to the Bens and we had written the code and it ran and we had the result, there came the natural question of what do you call the paper? And it was mentioned that a good name would be this, Floxy-Norsy-Nilahilipilification. I can't say it properly. And the reason we chose this is kind of like an in-joke. We were going to put this as part of the main title, just part of the title, but we decided to call it just this, and then PRL or PRD, where we ended up publishing it, came around and said, you know, you can't really name a paper that like that. It's not very descriptive. So we had to call it semi-simple extensions of the standard model gauge algebra, which is not as exciting, in my opinion, as Floxy-Norsy-Nilahilipilification. So if you want to know what this word means, Floxius, or the Floxy part, comes from the word a wisp. Norsy comes from the word a trifle. Nilai comes from the word nothing, and Pili comes from the word a hair, and it's a concatenation of those words with vacation on the end. So if you ever want to find this paper on the arXiv, you just need to search for that word. You just have to remember how to spell it. You have to remember what the word is. And if you do, you'll get 5 papers. Now, 2 of them are authored by me. There is this paper, the one I'm talking about, and there is, I'm speaking a bit quick, so I'll slow down in my whatever it's called, my pace of my speech. There is another paper, which is authored by, again, me and 2 collaborators, which is a self-citation of this paper. And there's a paper on the word length of word distributions, which is somewhat surprising given this is a long word. There's a paper, this top paper on machine learning. I don't really understand this paper. I tried to read it. I don't understand what it's talking about. And then this paper, I would show you on the mouse, but I can't get my mouse to work on Keynote. So this is why I'm having to talk through things. But the last from the bottom paper, you can probably tell from the date what sort of paper that is. And this is an April Fool's paper. So Godwin's power law is that as a conversation on the internet proceeds in time, it will naturally diverge to a given topic, something like philosophy. Then there's a quantum version of this law, which is what this paper is about. It's an April Fool's paper, that once quantum computers are developed, the rate at which you reach this will be increased. Okay, so that's the end of the brain break, and we can now proceed onto the second half of the talk. If you've watched the first half and you didn't understand any of it, now is a good time to try and rejoin me. I'm going to be talking about something slightly disconnected from the first half. It's going to be related, but it's going to be in isolation. So let me show you some sightseeing. This picture is a picture. I didn't take it. It's stolen from the internet, stolen from Google Image, Google Street View. This is in New York, and it's not this big building, which I've heard is quite famous. It's not that big building that I'm interested in. It's this other thing, this Build-A-Bear workshop. Now, if you've ever been to Build-A-Bear workshop, it's pretty cool. I was never actually allowed to go as a kid, but I always wanted to go. You walk in and you basically pick a bear. You pick the outside of the bear, and then you fill it up and you sew it, and you end up making this bear. So we're going to kind of do the same. We're not going to do Build a Bear workshop. We're going to do Build a Gut workshop. We're going to build a gut, and the outside of the gut, the structural components, the skin of the bear. We're going to take that from the list we had before. So let me just give you a sample of some of the guts that we had in the list I discussed in the first half of the talk. These are the simplest, and for the free family case, let me discuss what I mean by the simplest. I mean that they have the fewest representations of fermions. So you notice the first one, this has one representation of fermions, and the other three, they only have two. And these are the only ones which satisfy these conditions. All of the others have more representations of fermions than these. The first one is particularly boring. It's only got one representation of fermion, but it's like SO10 plus an SU2 or an SO3 flavor symmetry. So it's not that particularly interesting. So we're going to ignore that just because, that's not the most interesting one of these guts. Now, the other three, they're all based on Pati-Salam. So Pati-Salam, if you don't know what it is, it's SU4 plus SU2 plus SU2. And what these are some flavor combined version with Pati-Salam. So the first one, you've taken your SU4 of Pati-Salam and you've combined it with like an SU3 flavor symmetry. The second one and the third one, you've taken the electroweak sector of your Pati-Salam and you've combined that with like an SO3 gauge symmetry to get these SP6 and SP6, or in the case of the third one, SP6 and SO6. Right, so we want to choose one of these. We have to choose the one which we think is going to make the best gut at the end, which is going to make the prettiest bear. And when me and Joe DeFigi, the person I did this paper with, were trying to choose a gut to work on, we first went for the top one, this SU12, or the second one down, this SU12 plus SU2 left plus SU2 right, because that looks kind of nice. It's fairly simple. Everyone knows what SU12 really is, and everyone knows what SU2 is. It turns out we couldn't quite get this to work, so we managed to, get the gut, we put the filling in, we tried to sew it up, and what we ended up with was quite ugly, so we threw it away and hid it from the world, never to be seen again, until we work out if there's a good way to do it, or if someone works out if there's a good way to do it. We then went to the second one down, this SU4 plus SP6 left plus SP6 right, where you have like electroweak unification with the flavor. And this works quite naturally. So this is the one that I'm going to talk to you about. We ended up getting a pretty gut at the end. It worked for the thing that we wanted to do. So this is the one I'm going to talk about. We could have gone for the last one, this SO6 one. It probably give you like the same qualitative or quantitative results. But I'm going to focus on the one that we actually did in the paper. Now, I know what you're all thinking, right? You're thinking, what is SP6? SP6 is not one of those guts you really look at school or at university or wherever you learned group theory. SP6 is one of those ones that you see sometimes in the paper, but no one really knows what it is. So let me define it. I don't need you to remember the definition. I just need you to acknowledge its definition. I need you to be prepared that this definition exists. And this definition of SP6, so I'm going to define the group, and then the top one is the group, the bottom one is the Lie algebra. So SP6 is defined as the subalgebra of SU6 such that this set of equations, this trace equation, is satisfied. And there are different ways to define SP6, but some people don't define it as a subalgebra of SU6. For what we need to do, it really does need to be a subalgebra of SU6. So this is one definition. And then you can define the Lie algebra as a subalgebra of SU6, given these conditions are satisfied. Like I said, you don't really need to know this. I just wanted to complete the argument, let's say, by giving you the definition of SP6. It's also only defined for even n, so there's no SP5, for example. If you look at this, the definition, you can't really generalize it for odd n, so it's only defined for even n. Okay. Right, so we have our gut, and we've chosen like the outside. We've chosen the SU4, SP6, SP6. We've chosen that as our gut, and we have some fill-in to go in it. We have some fill-in to go in our bear in the analogy. In other words, we've been given the fermions for free. Like that came free. They said you have to take these fill-ins, but you can have some others. And the other fill-ins that we can put in are the scalar content, because I haven't said anything. Remember, one of my last key points of the last half of the talk was that I have not specified the scalar content. So let me specify the scalar content that we are going to choose for this model. And I've done it in a way where you've also seen the symmetry breaking pattern, because something which is quite cool in this model is that all of the scalars we need have a role in the symmetry breaking pattern. So there are no scalars that we need on top of the ones that we intrinsically need to get the symmetry breaking pattern to work. So these are the scalars we need to get the symmetry breaking pattern. Now I realize looking at this slide, it's like, whoa, too much information. Wait till you see the next slide, that's even more information, but let me just go through this slowly. Right at the top, you have SU4 plus SP6 plus or times SP6. I've secretly gone to Lie groups times SP6 times SP6. And we're going to break that using these fields S left and S right at the scale lambda left, lambda right to this intermediate group. So basically what has happened here is the SP6 right and the SU4, they have broken to SU3 and then this SP6 for right and this U1 right. So they are broken by this S right into that. And then S left or SL breaks the SP6 left down into this combination of 3 SU2s, one for each family. So it's like we're deconstructing the SP6 and then we're going to reconstruct them in a second. We then break down to the standard model using 2 fields, psi left and psi right, each of which sit in the 14 representation of the standard of the not the standard model of the gut. So they sit in the 14 representation of the corresponding SP group. That's basically the anti-symmetric representation of this SP6. And then we break down to the standard model, not with 1 Higgs, but it's not to standard model. We break electric weak symmetry, not with 1 Higgs, but 2 Higgs. And the reason we need 2 is because we need them to get the fermion masses right. It's a well-known fact, well, it's probably not well-known, but it's a fact that in things like Pati-Salam, you need 2 Higgses to get the fermion masses to work. Who knew? Some components of these Higgses are actually going to be heavy. So once we've kind of like broken the symmetry, the Higgses have some heavy components. And we're going to say that they're integrated out, those heavy components of the Higgses, at the scale lambda h. And this is kind of like where our structure comes from. And then we're going to introduce epsilons to represent the scale of this psi left or phi left, phi right breaker. So epsilon is roughly like the ratio of the scales of this, the scale where the Higgs is integrated out compared to the phi left, phi right scale. So I hope that all makes sense. I don't have the benefit, given this is a video and recording, to tell you or understand if you're losing this, but I hope all of this makes sense. Okay, right. So we have the scalar content, we have all the fields, and we have the fermions, so we have the symmetry breaking pattern. We basically have all of the fill-ins of our gut. We have all of the fill-ins of our bear. If we're going back to the build a bear analogy, build a gut analogy, we have all the fill-ins. And now what we need to do is we need to sew it up. We need to make sure we're going to do it right. And the thing that we are gonna the thing we're gonna try and get to work, let's say, in the next half of the next part of this talk is we're gonna try and get the fermion masses to work. There are a number of things we could do at this point. We could go down the neutrino masses route, or we could go down cosmology route. We could go down a number of different routes of what sort of things we want to look at now, but we're gonna sew it up, or do like different types of stitches of your bears, really, to how you're going to stitch it up, what you're going to look at to make a complete paper, complete model. And what we're going to do is we're going to stitch it up by looking at the fermion masses. Okay, now this is the slide where I was like, be careful, this is a lot of information. I'm going to walk through this slowly. That I realize this, looking at this is slightly overwhelming. So let's go very slowly. What I'm trying to tell you here is how our model predicts the structure of the Yukawa matrices. Okay, and this middle row gives the Feynman diagram, which contributes to the free component of the Yukawa matrix. And I'm looking at the down type quarks here. The charged quarks and the charged leptons and the up-type quarks work in exactly the same way. But for the free component of the Yukawa matrix, it comes from this diagram. So let me just tell you how or where this comes from. So if you take this middle diagram, this blue line is basically the color line for the sp6 right, and the red line is the color line for the sp6 left. Notice in each case for this middle diagram, they have 3 arrows on it, and those 3 arrows, they basically tell you that you're looking at the third family. Okay, that's all it really tells you. And if you look at the top row, this is kind of like our dictionary of what can happen, what can go into one path and out of it. So notice the Higgs, the only thing up here is 3 arrows in and 3 arrows out. So this middle thing, you can have this diagram, and this is going to give you order 1. Okay, it's going to give you a Yukawa proportion to the fifth and all of that, but it's going to give you like an order 1 number relative to the other Yukawa terms. If we go down and we look at this second line of Feynman diagrams, these are the ones that correspond to the 1, 3 element. So notice that the last red line, the red line going into psi left, it's got 1 arrow. So that means it's the 1 component of the left-handed side, and there's 3 going from psi right. And remember from the diagram at the top, the Higgs can only take in 3 arrows, and it can only give 3 out 3 arrows. So you have to convert the 3 arrows on the left to 1 arrow, and you do that using the psi lefts, and psi lefts come with epsilons. So you get that this 1, 3 component is proportional to this combination of epsilons. Remember, I was saying the epsilons basically give you a measure of the scale of the break-in, of the electroweak break-in. Sorry, of the breaking of the phi's compared to the integrating out of the Higgses. And then the same with the 2, 2. You kind of want to turn 2 lines into 3 lines in both cases. So you need one phi left and 1 phi right in both cases to get this 2, 3 component. Oh, sorry, to get this 2, 2 component. Okay, that was a bit complicated, but what I'm saying is, if you didn't understand that, you just need to remember, you just need to think that the Yukawa structure that we get at the end looks like this, where the epsilons are some small numbers related to the fifths. Okay, they're small numbers, and these numbers are at the minute 3 parameters. We can choose them as long as they're small. Okay, so we have this, and we've sewn up our bear, we've sewn up our gut, we have the Yukawa matrix, and now we need to take it to the school playground and compare it with our friends. Now, our friend happens to be an experimentalist, and we're trying to compare our theory bear with the experimentalist bear. And your experimentalist friend is like, you know, the quark masses and the third family masses, there's a hierarchy in them. There's a hierarchy in the masses. And you're like, okay, does my bear have this property? Does my the experimentalist is holding up their bear and says, look, it has these mass hierarchies, and you're trying to show that your bear is just as good, also has those hierarchies. But we do, so we can find the mass matrices, the masses of these from these Yukawa structures, and they're the same for the charged leptons and the uptype bulk system. The order 1 numbers are different, which I've ignored, but they're the same. And you can show that the first family, you have a mass matrix proportional to 4 epsilons, which is small. The second family is proportional to 2 epsilons, which is small, but not too small. It's not as small as one family. And the third family is proportional to unity. Of course, I'm missing some like phi squared here. So we get this hierarchy. As long as the epsilons are small, the first family is going to be smaller than the second family, and that's going to be smaller than the first family. So this is looking good, right? We can compare our gut to experiments. We can compare this part of the gut, like the foot of the bear, let's say, to the experimentalists. The foot of the bear, the experimentalist. And then your experimentalist friend is like, sure, but from these Yukawa matrices, you can get so much more than just the masses. You can get the CKM matrix. And you're like, sure, I can get the CKM matrix. So you go away and you do the perturbative analysis on your gut and your bear to get the CKM matrix. And this is what we get. So let's just ignore the matrix on the right for a second. We get this structure. C1s, C2s, they're just order 1 numbers. We know what they are, but they're order 1 numbers. They're in terms of the potential parameters that I haven't written down. But we have this structure in terms of the epsilons. So let's have a think. Let's set epsilon left 1, 2 to be lambda, and let's set epsilon left 2, 3 to be lambda squared. If I do that, I get this rough structure with the lambdas in it. Okay, and this looks very like the CKM matrix. Okay, so it has the same structure as the CKM matrix. But then your experimentalist friend is like, yeah, it's got the same structure, but what about the numbers? Can you get the numbers in the CKM matrix right? Can you tune the potential parameters so that these order 1 numbers, these C1s, C2s, etc., come out and match closely with experiments? And as a theorist, I go away and we go, okay, right, so we have to fit now. We have to fit the masses of these. We have to fit the quark masses. We have to fit the up-type quark masses, the down-type quark masses, the charged lepton masses. These all have order 1 coefficients in them. Independently, we need to fit the CKM matrix. And we need to ask, is there enough freedom to do that? Do we have enough freedom with these order 1 numbers to mean that we can have these differences between them and still work? And the answer is yes, subject to the condition that these equations hold. So if these equations hold, then yes, we can fit all of the masses. We can choose the order 1 numbers I've kind of left out. We can fit those to match with the standard model. Now, your experimentalist friend is sure you can fit them as long as they satisfy these conditions. Do they satisfy these conditions? And you're like, okay, fine, I'll go away and I'll check if they satisfy these conditions. And you can show that they do to a fairly good degree of freedom. The J here is just log invariant. It's a measure of CP invariance. So right, let me just recap a second what I've done, because this is a lot of information, and I just want to basically say the main result, that we can form a gut using this SU4 cross SB6 cross SB6. We can give it a scalar sector, which has to require symmetry breaking. That scalar sector can alone induce the Yukawa structure on your matrices, which give enough freedom and give the right sort of scaling for your fermion masses and the CKM matrix. So you can kind of predict the fermion masses, fermion structure from your CKM matrix. Sorry, from this gut. Good. I should say the CKM matrix only determines the left-handed epsilons. So you still have the right-handed epsilons free, and you can use that in the masses to set the right ratios between the first, second, and third family masses. Good. Hopefully that was all fairly understandable. Now the question is, what about future work? So there are a number of things we wanted in the future. Look at low scale unification. At the minute, we assumed everything was high scale. This model doesn't have proton decay, so you can imagine the scale of unification being brought down to a lower scale. We want to study flavor dependent forces in relation to the B anomalies. So this is one of the routes that we could have gone down. We could have looked at the B anomalies, and this is something we want to do in the future. We could look at neutrino masses. We actually do know how to get these to work. It's just complicated, and we didn't go into detail. We didn't want to put it in the paper because the paper was really nice by itself. At least we thought it was. So we didn't end up looking at the neutrino masses. And the last one, cosmological consequences, is a whole broad study. It's been done for other guts, and we probably can be done for this gut. So what are the 3 things you want to take away from this talk? The first is we have electroweak flavor unification. We've unified flavor and the electroweak symmetry. The second is it predicts the structure of the CKM matrix and the masses. And the second is the third is rather, there's exciting possibilities for future work. So with that, I end this talk, and I hope you enjoyed it. If you do have any questions, I'm going to put this online, so put it in the comments and I'll try and answer. I realized the last half was probably a bit quick, but I apologize for that. Okay, thank you. I have to work out how to stop this now, so you're going to have to watch the awkward bit where I